Good morning, Astronomy 1020. You just missed a pretty funny intro, but that's okay. Astro Bro is in the house for the final lecture, and we're going to talk to you guys about supernovae and black holes. I know the night class missed all of that. I was having too much fun. All right. What are we going to do today? We're going to talk about supernovae. We'll talk about black holes. And then we're going to punch out early. We're not going to do a 13th homework because Astronomy 1010 only did 12 homeworks. So I figured it was only fair if you guys kept the same schedule. In fact, with 12 labs and 12 homeworks, I think we did a good job. Hey, that means a couple of administrative things to think about. Oh, we want to talk about that, huh? Actually, the class is supposed to be stars and galaxies, and it kind of just ended up being mostly stars. But I threw in little tidbits about galaxies when I could. It takes a long time to cover these subjects, right? Administrative stuff. The first thing is today or this week, we only had a lab, right, Caitlin? A lab that you have to do? Okay.
My computer was not my friend, all right?
Oh, Professor,
Okay.
we have beef as well.
Oh, really?
Huge beef, yes.
What's up?
It's mostly my fault. However, I'm going to put the blame on you so I feel a little bit better about myself.
I don't know if that's how this works then.
I couldn't submit the lab and the thingy.
I gave you a full day to do it, and I told you I was closing it out at night.
I went to do it, and it didn't work.
What time did you do it?
I don't know, like afternoon, evening, but not night.
No, because that day, I graded papers that day at like 8 or 9 p.m., which is exactly what I said I was going to do.
I'm not buying that.
Well, what do you have to submit?
It's the most recent one, 11, I believe.
Homework or lab? You're not being clear.
Both.
Email it to me and I'll consider taking pity on your soul.
Okay.
All right? Email it to me and I'll consider taking pity on your soul.
Thank you.
All right. Well, Elijah, no, the band doesn't have any shows. We just played a show at ISCO on November 13th, and I think considering the fact that Rhode Island is #1 in coronavirus cases right now, that'll probably be the last show that we played for a while, unfortunately. I'm kind of bummed about that. But hopefully this vaccine will come out, spring. I know spring 2021 is already online, thankfully. But I'm hoping that when the weather gets warmer, that the vaccine will get more properly distributed and we can get back to fun. So deadlines for things, which Austin, cover your ears because you're not going to listen to them anyways. The deadline for this for reals is going to be like Friday or Saturday for the homework. Okay, Caitlin? Because after Saturday, I'm going to finish the final grades and then it's pina colada time. Okay, then it's see you later, bye. And the class has to end at some point. And I'm going to try to make Sunday the day where
I got you.
You got that? You got that? I know the printer wasn't working. Get something into me, okay?
Yes, sir.
Okay, I like it. And other administrative things. Could you guys please, well, if you would like to, don't forget to rate the class by filling out a student rating of instruction. I forgot to make this a big point last semester, and like one person gave me a review. So yes, I am teaching 1010 in the spring. I would love you guys to come back and take the other part of the course. The two parts of the course have a similar beginning, like the trunk of a tree, and then they split out about midway into different directions. One does stars and galaxies, the other does planetary science and things in the solar system. They're both a ton of fun, at least I think so. Austin, I'll think about the override. Because listen to this, the administration at the start of this semester doubled all of the faculty members' enrollment. So we went from 14 students per class to 28 students per class. That is a huge amount of additional work for us. And so in solidarity, we're already stretched to the limit. So it's going to be difficult to give people overrides because one, of the sheer number of students, and two, because of the camaraderie and the brotherhood of professorship. But Austin, you can send me your student ID and I'll think about it. I'll see what I can do. I certainly like it when students who've taken the 20 class, come back to take the 1010 class, because then you guys are an inspiration and a help to other students in the class. You kind of know what's going on, and that helps the students who are less experienced. So it's good if
Or
it
you
works
do it
out.
reversed and like how I did.
Right, yeah, exactly, Chris. So, and a couple of you, Chris, you're one of the few people who's had the experience of learning with me live and learning with me online. So that's kind of interesting. Oh, you're done, Stacy. Congratulations. Hey, yeah, another pep talk for you guys before we get into it today. I know that learning from home, from your bedrooms, has been stressful and tough for a lot of you guys. When I talked to my former students, they said they were really struggling getting their work done. It's kind of paradoxical. You'd think you'd have more time to do it, but it's hard sometimes to stay focused in your bedroom. But this is the perfect time to be in school and to level up your video game character before you go out to battle the top bosses, who will probably be someone in the corporate world. So you want to have your video game stats leveled up as much as possible, and this is a good chance to grind it out, to learn some good skills, take classes, get those credits out of the way, and then when the coronavirus is over, you'll be ready to go out into the world and get some cool jobs and do some fun things. So keep at it. Don't give up. It's hard. It is hard. I know. But you got to try to have fun and get into it. And luckily this is a fun subject, so we don't have to try too hard. Oh, so for those of you who don't know where the student ratings of instruction are, I'm not entirely sure how it works on the student end, but on the faculty end, where am I here? I would go to my CCRI, and when I want to read them, I go to my for faculty tab. So you'll probably go to the for students tab. And on my faculty tab, they are down here under student ratings of instruction. And then I can click on that and I can see the things that people leave for me. Well, there's nothing yet for 2021 because you guys haven't filled it out, but go ahead and do that today at the end of class or something.
Professor, I filled mine out.
Oh, that's great.
Well, yeah, but why aren't you seeing it?
Oh, I know why. Because usually there's a lag. Usually they don't show them to the faculty. Oh, that was 2021. They usually don't show them to the faculty anyways for at least a semester, so that there's a little buffer between the administering of grades and the checking of reviews. So I will see it eventually. Okay, that's great. I love it, Gianna. 39 million, wait, how many, what is this? Well, that's, 392 billion out of 10. I love it, I love it. Okay, you should probably put that in scientific notation though. Anyways, let's have a think about black holes. Let's have a think about supernovae, and let's go to our lecture on stellar death. So remember that we have 3 different mass categories of stars, and we have, let's go to my board notes here, and let's lock on me. Okay, so we have low mass stars, and then we have high mass stars. And today we're going to focus a little bit more on the high mass stars. Actually, guys, if you don't mind, can you give me just like a 2-minute pause here? I'm actually overheating in my Astro Bro costume, and it's not me. Just, I'm going to stop the recording. Give me. Thanks, guys. Sorry about that. All right. So, no. Well, it's the last day. Some hiccups are allowed, I think. I want to spend some time talking about supernovae because they're cool and they're interesting and they're an important tool that astronomers use. And it's confusing because both high mass and low mass stars can produce supernovae. And there's some things that are worth knowing about and taking down some notes for. I know. Let's remember that a low mass star goes through a death cycle that has 2 parts. The death of a low mass star forms a planetary nebula. That's the outer layers of the star that turn into a big, beautiful gas cloud. And the inner nuggets, what was formerly the nuclear core of the star, forms a white dwarf. Students, you remember what a white dwarf is typically made out of, correct?
Carbon.
That's right, carbon. Although there are ones that are made out of mixtures of carbon and oxygen, but we don't have to get into that today. On the other hand, for a high mass star, there are several other possibilities, right? So when high mass stars go through their death cycle, they rupture in a violent explosion called a type 2 supernova. Frequently, these are referred to as high mass star supernovas, but the technical term is a type 2 supernova. And they leave behind one of two possibilities for the remnant that was once their core. This is something that you already know. We've already discussed this, but I'm starting here with something that you know. If they're on the lower end of the high mass spectrum, they will leave a central core behind, which is a neutron star. And neutron stars typically have a mass somewhere between 1.5 solar mass units all the way up to a theoretical maximum, or an observed maximum of 3 solar mass units. And then if the center mass is too great, you cannot halt the gravitational infall, and you will create a black hole. Those usually have masses greater than 3 solar mass units, but it is possible in theory to construct smaller black holes. And we'll talk about that today as well. Now, if you're white dwarf, okay, so let's talk about a couple of different issues. What is the difference between a planetary nebula and a type 2 supernova? At first, it looks like in both cases, the star is undergoing an explosion. And that's sort of true, except the explosion is very gentle when it's a low mass star death. Here you can see gas being driven off of a low mass star, and eventually this gas will dissipate and become something like the Ring Nebula or the Cat's Eye Nebula, one of these things. Technically speaking, people make a distinction when they talk about explosions between a rapid expansion of gas and then what is called a detonation. If you think about your favorite action movie where there's some big explosion and you hear the kaboom is what's called in physics a shock wave. And that's when you sort of try to push gas faster than the speed of sound in a medium. As you guys know, it takes time for sound to go from my voice, from my mouth, to the speaker to your ears. And the speed of sound at standard temperatures and room densities is 340 meters per second or something like that. That's the speed of sound on planet Earth at sea level. It is possible under violent circumstances to push gas faster than the gas wants to move. And as an example of that, perhaps we could show you something, some cool pictures or videos from the internet. Actually, I have some in my slideshow, but let's share the screen here. One thing that you can do is you can take a picture. Let's see if I have them in this slideshow. You can take a picture, sometimes using infrared cameras, of a bullet traveling at supersonic speeds. And when a pistol is fired and you hear the report of the pistol, you are experiencing what's called the shock wave. And this is a hallmark of what makes an explosion. You're forcing this bullet to travel faster than the speed of sound, and it sort of becomes like a snowplow for air molecules. What you can see in this image is you can see this structure, which is known as the bow shock. And this is a super, super thin layer of really, really dense and super, super hot gas. So whereas the density of gas particles, it would be nice if I could, might be sort of spread out over here and over here. Within the bow shock, the particles are really pig-piled on top of each other, and they're extremely, extremely hot. And the bullet is basically forcing them through the air. When you hear this, you hear the sonic boom. And you can hear the sonic boom in a number of different ways. When Indiana Jones cracks his whip, whoosh, the end of the whip is actually breaking the sound barrier and creating a little shock wave. The report of a pistol, Obviously, you might have heard about supersonic jets before. They can travel faster than Mach 1, than the speed of sound. And I have a picture of that in my next slide. They've got some cool YouTube videos of the sonic boom. You might get to see this at an air show. Notice that you can see the bow shock there, and you can see the condensation as the super dense, super high temperature layers basically condense moisture along the bow shock. Hell, even if you take a ruler, right, and I could try to demonstrate this against my chalkboard here, that is technically considered an explosion or a shock wave, that hard snap that you hear right there. Why am I telling you this? Because one of the differences between a high mass star supernova and the death of a low mass star is the low mass star isn't so much of a detonation during the explosion. It's more of just like a smoke ring, like a gentle puffing out. The high mass star supernova is a very violent experience. And you can see that when you look at these legendary, these are called supernova remnants. Sometimes thousands or even tens of thousands of years after a high mass star has exploded, you can take a powerful X-ray telescope, which is very good at detecting the hot ionized gas, and you can image one of these supernova remnants, and you can see a bubble of hot ionized plasma expanding out into space. This gas was once part of the body of the star itself, and it's now dissipating into the galaxy, where it will eventually cool, settle down, and form another generation of stars from the enriched metals that were part of its body. So basically, a simple cartoon way of looking at it is a type 2 supernova is a bona fide explosion, whereas the formation of a planetary nebula is not quite like that. It does not exceed the sound barrier in the medium. However, a high mass star supernova is not the only type of supernova. Remember that if a white dwarf is in isolation, it will eventually cool down into a carbon cinder and disappear like some sort of stellar skeleton in the galaxy. But remember, half the stars in our galaxy are part of a binary pair. If your white dwarf becomes part of a high mass transfer binary, and when astronomers are feeling lazy, they call them HMXB, high mass transfer binary, you can frequently have the situation that I described. And here I'm going to erase this for a second. Anyone mind if I take this bottom part off? Okay. In those situations where you can have a binary star with a red giant in a companion relationship with a white dwarf, it is possible for the red giant's outer material to feel a slightly stronger gravitational tug from the white dwarf than it does from its parent star. And that's just because the star is swelling out to be like 100 solar radii or something. It's so big. And of course, that's when you form this accretion disk. Once again, this is all review. This is stuff that I've told you before. But I'm going to present it in new context today, so bear with me. Remember that as material spills onto the white dwarf has a problem. It's held together by electron degeneracy pressure. So in a normal plasma, F532, the electrons are dissociated from the nuclei. So this could be hydrogen gas that's turned into a plasma. The little blue pellets represent electrons. The red pellets represent protons. And they're all kind of swimming around together. The gases are not quite like ping pong balls in a box because they feel electric currents and magnetic forces. So the electrons tend to kind of, let's try to do that again. Let's erase that. The electrons tend to kind of move away from one another. They sort of try to move towards the protons, and the protons are doing a similar kind of thing as well. But it ends up being that the electrons and the protons move somewhat independent of each other. Notice, however, that in a normal plasma, the distance between electron and proton, the distance between electron and electron is quite large, many times greater than the size of the particle itself. In other words, it's mostly an empty box. When you create a white dwarf, or when you create a neutron star, but let's start with a white dwarf, you pack the plasma uncomfortably close together. The electrons are still much too high temperature, much too high kinetic energy for them to remain bound to the protons, but they're zipping around in this very densely packed soup, and they suddenly find there's not much more room for them to wiggle because they're getting uncomfortably close to their electron brothers. Eventually, this thing called the Pauli exclusion principle kicks in, and it's a quantum mechanical theory that tells you that no two electrons can have the same quantum state. You probably heard about that in your chemistry class when you had to have electrons with spin up and spin down in each energy level. I don't know if you guys took chemistry. If you didn't take chemistry, fine. Maybe a sillier way to imagine the Pauli exclusion principle, and this is a vulgarity, but I'm going to give it to you anyways. Just imagine it as the electrons are getting pressed up against one another, and they have nowhere left to move. That's how you could think about degenerate electrons. The problem with a white dwarf, it doesn't have fusion, so it's fighting back against gravity through electron degeneracy pressure. And because of that, when you add more matter to a white dwarf, the white dwarf tends to get smaller and compress the electrons even more. So here's a cartoon of what I'm talking about. In a high mass transfer binary, bits of fresh plasma start to spill onto the surface of your white dwarf, and the extra plasma adds mass, and the mass adds gravity. But all that's fighting back against gravity is the electron degeneracy pressure, and it does not have a relationship between temperature and pressure. As you squeeze the thing and heat it up, it doesn't add more pressure. And this causes the star to contract and contract. The genius of the legendary astrophysicist Chandrasekhar is he realized that there had to be a breaking point to how much you could squeeze a white dwarf. And he used Einstein's theory of general relativity to predict that if you continued to squeeze a white dwarf, it would eventually hit a breaking point known as the Chandrasekhar mass limit. I talked about it before. I want to talk about it again for a second. If a white dwarf exceeds a critical value, a mass equal to 1.4 times the mass of the sun, and this has a legendary name in astronomy. It's called the Chandrasekhar. Okay, I'm going to spell this badly, but I'm going to try. Chandrasekhar mass limit. This is reached when the velocity of the free electrons approaches c, the speed of light. At that point, you cannot squeeze the white dwarf anymore because you will violate one of the principal tenets of relativity, which is nothing can travel faster than the speed of light. And do you guys remember what happens if you add one more little drop of plasma onto your white dwarf? That's right, Arunsak. Kaboom. You create a different type of supernova. Here's where we get to the new stuff, okay? If you exceed the Chandrasekhar mass limit, you will create a very dramatic explosion called a type 1a supernova. Okay, I want to go off-road for a second on the Chandrasekhar mass limit, and I want to attempt very briefly to talk about something that's over our pay grade. One of the things you have to do as like a senior and an astrophysics major is usually have to take a course where they force you to attempt to derive the Chandrasekhar mass limit and go through the legendary analysis that Chandrasekhar himself did. It's intense. But I want to show you what the result is because it's considered one of the most beautiful equations in astrophysics. And I think that you guys might be able to appreciate this, or at least I'm going to try. And if you don't think it's interesting, then I apologize, but let me give it a whack. Let's go to the Chandrasekhar mass limit, and let's just check out the Wikipedia page. I don't believe that they do the entire derivation there, but they show you the final answer, the answer that you're supposed to get as a student, and the same one that Chandrasekhar got. It turns out that when you input the density of the white dwarf, and you take into account the velocities of the electrons, and you set them equal to the speed of light, all of the other variables disappear from the equation. And the reason why you get 1.4 solar masses is you end up with a formula that says the upper limit to the white dwarf is all of this scary looking junk. But what's interesting about all of this scary junk is every variable that you see in this equation, they are all constants of nature. They're not numbers that humankind makes up. They are numbers that are sort of encoded into the machinery of the universe. And I bet you guys might even recognize some of these from our class. This is kind of like a tour of what we learned about. What does the big G represent, class?
Gravity.
That's right, so we know gravity's involved. What does C represent?
Speed of light.
And that tells us that this is a relativistic equation involving relativity. How about H? Do you remember what H is?
Is it Planck's constant?
That's right. We saw that when we dealt with photons. Usually when Planck's constant shows up, it's considered a symbol of quantum mechanics. So we can see quantum mechanics, relativity, and gravity all coming together. The only other variable of interest here is the mass of a hydrogen atom, which is also fixed. And the rest of these are just mathematical constants. So in a weird, crazy way, I don't need to personify the universe, but the universe itself has fine-coded and tuned the upper limit to a white dwarf. And because of this, people think it's kind of a beautiful result in astronomy. I hope you guys can appreciate what I'm talking about here. It's an answer where you didn't input any variables, but the fundamental constants of the universe itself have coded in and set the upper limit to a white dwarf. Now, what I want to ask you guys is this. Let's consider our two types of white dwarfs. Let's consider our two types of supernova side by side for a second. And see if you guys know enough astronomy to predict the differences between the two. So we have a type 1a supernova, and we have a type 2 supernova. Remember, a type 1a supernova comes from a white dwarf at the, I'm just going to abbreviate Chandrasekhar as Chandra for obvious reasons, at the Chandrasekhar mass limit. And that's when your mass is equal to 1.4 times the mass of the sun. A type 2 supernova, on the other hand, comes from a high mass star death. Class, what is the mass range for high mass stars? You were able to answer this last time.
8 solar masses to 100.
Excellent. You guys know your astro. I'm very proud of you. I don't even need to give you a final exam because you are so well versed in the fundamentals of astrophysics, okay? Now, Arunsak, which do you suppose would be the more dramatic supernova? The supernova at 1.4 solar masses, or the supernova that can happen anywhere between 8 to 100 solar masses?
I would imagine the heavier stars would be more dramatic.
And I would have imagined the same thing, Arunsak, and guess what? We would both be wrong. It turns out that these are the wimpier supernovas. And I know that's hard to understand, but you have to understand the power of relativity. These happen when you push electrons up to the speed of light, and that just makes things go haywire. Believe it or not, the type 1 supernova are more violent. not only are these more violent, but there's something really magical about type 1a supernovas. These can happen at a range of luminosities. And you might ask, why am I talking about the luminosity? Because we only see a supernova when we see the light from the supernova. But a typical luminosity for a type 2 supernova would be something close to 1 billion solar luminosity units. And I'd like to remind you, it's a dramatic picture that you've seen this before. When I showed you guys the legendary, the legendary supernova 1987A. Sorry. Bear with me, friends. Once again, function F5. Remember that there are these small dwarf galaxies that orbit the Milky Way. Here's a picture of them on the sky. On the right, you have the Large Magellanic Cloud. On the left, you have the Small Magellanic Cloud. These are actually considered galaxies, but they're a very weird type of galaxy called an irregular galaxy. They're small. They're almost like the bunny that's sitting in your lap. They're kind of like a little pet to the Milky Way. This star underwent a type 2 supernova in 1987, and what you can see is the light emitted from the supernova rivals the entire nucleus of the galaxy, which is probably the combined light of close to 1 billion stars. So you can see right in this picture that the brightness of the single supernova is the same as the brightness of the billions of stars that are mushed into the center of the galaxy. However, because the mass, the powder keg that goes into your explosion, can vary from 8 to 100 solar masses, this also varies. However, I'm here to tell you something important about astronomy. Because a type 1a supernova always explodes at the same mass, that's like saying your explosion is going to be based on the same number of sticks of TNT, right? If a stick of dynamite is a standard unit of nitroglycerin or whatever it is, if you have 5 sticks of dynamite, if they're regulated, you should always have the same power of explosion. And that's the case for a Chandrasekhar mass limit. You're always blowing up your white dwarf when it hits 1.4 solar masses. And for that reason, a white dwarf supernova always has the same luminosity. And the luminosity of a white dwarf let's call it a type 1a supernova, is always 10 billion solar luminosities. That is the brightest that a supernova can be, or the most luminous that a supernova can be. The brightness depends on how far away it is. Okay, first I want to show you a picture of a white dwarf supernova, and then I want to talk to you about why I'm going on and on about it, because there's a reason for this, okay? There's a famous white dwarf supernova, we see them all the time, that took place in a galaxy called NGC 4526. And here's the iconic photograph of it. We see white dwarf supernova go off all the time, but they are so incredibly brilliant that we can see them in distant galaxies, some of which are hundreds of millions of light years away. Now, I can't remember the distance to NGC 4526. Let's see if we can grab that really quick, because I'm a little curious to learn myself. So let's teach me something today. NGC 4526. And let's see, I'm sure there'll be a distance estimate to it, and I'll explain that in a moment. So this is 55 million light years. So I wasn't too exaggerating when I said hundreds of millions of light years. This is a half 100 million light years, right? So 55 million light years away. And in 1994, a white dwarf supernova went off. Now, How did they know that it was a white dwarf supernova? I'll explain that in a moment. But remember, when you look at the distances of 50 million light years away, you can no longer make out individual stars within the galaxy. All of the individual stars kind of smear out into a paste of light. And probably the first time you looked at this picture, you thought that was a star in the center of the galaxy. Oh, no, 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 no. That is the bulge of a galaxy. The bulge of a galaxy contains billions of stars, sometimes more than billions of stars. You can see that the luminosity of this 1.4 solar mass explosion is equal to the entire luminosity of the 10 billion stars within the bulge. It's absolutely insane that one star's explosion could rival the light of 10 billion stars. We can see them from amazingly far distances, but the reason that astronomers care so much is because if they always have a known luminosity, they become, wait for it, a standard candle. This is not the first time I've mentioned a standard candle in astronomy. This is a critical concept that I think everyday people should know about. Does anyone out there remember what a standard candle is? I'm sure not everyone does.
It was like a thing with a certain luminosity, so you can use it to measure other luminosities,
You're
right?
gonna skip my laptop.
Sorry, are you talking to us or are you talking to your animals? Oh, Caitlin's having some issues with her cat.
Oh,
Okay. We heard that. Okay.
Please tell the cat I love him.
Wait, so Christopher Leonard, you were so close to the right answer. It's an object of known luminosity, but you don't use it to find other luminosities. You use it to find. Yeah. Oh, she's unmuting it. I get it. That's great. Look at that little kitty. Yeah, we have to have some animals here for the last day, you know? Unfortunately, my raccoon has disappeared. I hope he's in some torpor or hibernation because I've really missed Buff the raccoon. What about the metal water bottles, Austin? Okay. It's not that you use a standard candle to find other luminosities. You use a standard candle to find what?
Distance.
Who said that? Who knows what the hell I'm talking about?
Cameron.
I'm sorry, one more time. Who was that?
Cameron.
Cameron, you, my friend, are cool. That's right.
I'm
The whole point of a standard candle is you use it to find the distance. And this is what the importance of white dwarf supernovae are today to astronomers. Literally a couple of years ago, a Nobel Prize in physics, the one that discovered dark energy, was based on measurements from white dwarf supernova. Remember that if you use the luminosity distance formula, and this would have been a problem on your final exam, so I kind of sad that you're not going to get to do it. You always know the luminosity of a white dwarf supernova. You measure the brightness with your telescope, and then you can use it to find the distance to the galaxies. You know, we wouldn't know all kinds of interesting things about our universe. We wouldn't know how old it is. We wouldn't know how fast it was expanding if it wasn't for the fact that these white dwarfs always blow up at the same mass. Thanks, universe, for hooking us up with a cosmic light beacon. Thank you for doing that for us. Otherwise, we would be ignorant savages clinging to a rock, playing our video games, not knowing how big or old the universe was, okay? This is important. Hey, one last thought, and then I'll move on to black holes, okay? Can you guys, I'm going to ask an advanced astronomy question here. Do you guys think you could predict differences in the spectrum of a type 1a supernova versus a type 2 supernova? Remember that when you take the spectrum of a star or a glowing object, you can see emission and absorption lines. This is made from a high mass star. This is made from the core, a white dwarf of a low mass star. What type of emission or absorption lines would you expect to see in a type 1a supernova? What type of emission and absorption lines would you expect to see in a type 2 supernova? Is that too tough a question, or can you guys handle that? What elements would a white dwarf supernova have?
Would it be
What
a
elements?
carbon emission?
You'd expect to see carbon and maybe some oxygen. But then again, there's definitely carbon and oxygen in a high mass star, isn't there?
Yeah, but wouldn't it also be mixed with hydrogen?
That's the point. Who said that?
I did, Paul.
Paul, you're right there and swinging for the fences. That's exactly right. These ones will contain hydrogen. These ones will not. And you did as good as I could have possibly asked for. When astronomers study the light curves, the way they tell the difference between a type 1 and a type 2 supernova, here's some sample spectrum. In the type 2 supernova, you can see this bright emission line in hydrogen alpha. That's that red line from hydrogen, which we learned about earlier. You'll notice that hydrogen alpha is not present in a type 2, but you can see oxygen and helium, and I believe sometimes carbon as well. You know, one of the things that I didn't know about until a couple of years ago, because I'm constantly learning new things about astronomy, is that during a type 1a supernova, usually the supernova will mostly destroy the white dwarf, but some of the white dwarf actually gets compressed into iron nuclei. The greatest contribution to the nickel-iron cores of all the terrestrial planets are all from white dwarf supernovae. White dwarf supernovae produce more iron than all of the high mass stars combined. So when I have this meteorite, this iron meteorite that formed Meteor Crater, didn't we talk about this last class briefly? This lump of iron was probably forged in a white dwarf supernova. It probably had a very violent origin, and then it floated around the solar system and eventually crashed into Arizona, and now it's in my hand. A very cool cosmic journey. Okay, all of that was to tell you that there are different types of supernova, and these supernova are really important to astronomers because we use them to measure the distances to galaxies very far beyond the Milky Way. That's all I wanted. Now it's time to talk about black holes. To talk about black holes, we might want to start by explaining one of the differences between calculations of white dwarfs and calculations of neutron stars. I'd like you guys to remember that a neutron star, we know that they have to start off bigger than the Chandrasekhar mass limit. This is when you compress your star into a ball of neutrons. But unlike the Chandrasekhar mass limit, there has not been another astrophysicist who has been capable of calculating the theoretical limit to a neutron star. Neutron stars are held together by neutron degeneracy pressure. But in theory, there should be a limit to how hard you can squeeze those neutrons. We believe from observations of neutron stars, this is what's called an observational upper limit. Meaning, because we have never observed a neutron star greater than 3 solar masses, we hypothesize that they cannot exist. The real reality about why we don't know the exact highest mass of a neutron star is because when you compress a mass of 1 to 2 times the sun into a ball that's only 10 kilometers across, the matter becomes so compact that you need the equations of general relativity to explain how gravity is interacting with surrounding space-time. Unfortunately, you're also packing together a bunch of neutrons, and particles like neutrons are described by quantum mechanics. For years, people have attempted to understand how general relativity and quantum mechanics fit together. This is the legendary quest for the elusive quantum gravity. To this date, physicists have not been able to come up with a consistent theory of how large masses will battle it out with quantum mechanical forces where particles act like waves. To do this, you would need a theory of everything. You would need all four forces to be describable in one single framework, and we don't have that yet. If you could come up with a theory of quantum gravity, you would be literally a master of the universe. You would win a Nobel Prize, and you would understand how every particle evolves from the Big Bang to the eventual heat death of the universe. So because we don't have this, we're a little uncertain what happens as we approach the limit where a black hole should start to form. However, do you guys remember that we calculated the escape velocity of a 1.5 solar mass black hole with a radius of 10 kilometers? And what did we get? Do you remember? Can you find that in your notes? What was the escape velocity? Well, anyone?
2 times 10 to the 8th meters per second.
And what was that as a percentage of the speed of light?
0.66 of speed of light.
Yeah. I thought about doing it as a calculation, but we have some other calculations to do today. If you were to have plugged in 3 solar masses, you would basically get that the velocity is equal to the speed of light. And that means once you hit the speed of light, not even the compression of neutrons can support the collapse against the star. When this happens, a black hole will begin to form. And what's fascinating is gravity will begin to squeeze your ball of neutrons. Gravity will continue to squeeze, and it will never stop squeezing. In theory, gravity can squeeze the mass all the way down to a point particle of 0 dimensions. And this is when you create a black hole. We're going to draw a little model of how a black hole works. A black hole, simply put, could be considered any object whose escape velocity is greater than or equal to c, the speed of light. Typically what happens is you have a collapse, a perpetual collapse, into a point particle of 0 dimensions, which is known as a singularity. And the singularity is the black hole itself. It's a particle of 0 dimensions, which sounds absurd, and yet this is what the theory tells us. However, there is a zone, an area, or a volume surrounding the singularity, which also has an escape velocity greater than the speed of light. And this is kind of like a shroud which covers the singularity. It's known as the event horizon, or the radius of the sphere is called the Schwarzschild radius. So this is an imaginary sphere which covers our singularity. Okay? The edge of this thing, this is an invisible boundary. There's nothing actually there. It's just that light can escape here. I want to make this really simple. So in this surrounding region, light can escape. Once you cross this boundary, light cannot escape. And this boundary, you've probably heard the term before, is called the event horizon. Okay? The radius of your event horizon, I'm going to call R sub S. And R sub S is something known as the Schwarzschild radius, the Schwarzschild radius. And in a weird way, it's kind of like the radius of the black hole. It's not actually the radius of the black hole. The radius of the black hole is 0, but it's the radius of the boundary surrounding the black hole. Okay, here are a couple of weed-smoking artist illustrations might help us imagine what it would look like. What if you came across one of these doodads on your cosmic trip through space in your spaceship? What would you actually see? You might see something like this. Was that 85? Nope. There would be a region of space which contains stars and maybe gas, but once you get close to that event horizon, pitch darkness, absolute nothing. In fact, the gravity becomes so intense, even at, so this is your Schwarzschild radius, at 2 to 3 Schwarzschild radii, while light technically can escape, the gravity and the curvature of space-time becomes so intense that literally photons will go into orbit around the black hole. Do you realize that if you were standing here and you went into orbit around a black hole, you could look forward and see your back because photons coming off your back could actually orbit around in a circle? Very weird shit starts to happen when you get close to a black hole. Not only do things go into orbit, but the coordinates of space and time themselves begin to rotate. They call this frame dragging or the lens stirring effect. If you try to put an object here and make it stationary, space-time becomes a river that will carry you along in a current surrounding the black hole. It's impossible to be stationary next to a black hole because the coordinates of space will drag you along in a current. Totally wild stuff. Now, as you approach the event horizon, you will experience an extreme form of time dilation, where at the event horizon, all time will seem to stop from an outside observer. If you are at the event horizon, you can cross it, but if you look back, you will see the universe evolve at a hyper-accelerated rate. You'll see stars go supernova, planets come and go and die. It'll be a pretty trippy experience, I gotta say. Remember that what's past this boundary is a region of empty space from which light cannot escape. The idea is that if light can't escape it, then neither can you and neither can anything else. So anything which makes the mistake of crossing this boundary, it just goes down the drain forever. To understand a black hole, one really needs to remember that in general relativity, we're talking about the coordinates of space-time being warped. So remember that we can think of space-time as kind of like this grid. This is 4-dimensional space-time. And that in general relativity, massive objects like a planet or a star, they curve and warp the coordinates of space-time, and other objects move on the curved space-time, and that's how gravity is supposed to work. Well, a normal star like the sun has a small amount of curvature surrounding its space-time. And this is the curvature that Earth wobbles along when it goes into its orbit. A neutron star curves space-time a lot more. And you need general relativity to describe a neutron star because the curvature of space-time becomes very intense surrounding a neutron star. But black holes, forget about it. A black hole is an infinite curvature of space-time. It's basically like taking a needle and puncturing a hole in the fabric of space-time itself. My friends, this is the ultimate Super Mario Brothers pit. Remember the Super Mario Brothers pit where you just fall down forever and then you die? That's kind of what this is like. Let's do a quick calculation. You know, I couldn't let you out the door without at least one little math problem. In 1919, an 18-year-old astronomer named Carl Schwarzschild used the equations of general relativity to calculate and derive a formula for the Schwarzschild radius, the radius of an event horizon. It was the only paper he ever published. It's considered a landmark work in astrophysics, and it's the only paper he ever published because he got drafted into the German army in World War I and got shot in a trench a few months later. It's so sad, right? But this one thing he did was profound. We cannot reproduce his original work. It's way the hell over our pay grade, but we can get his result by considering a simpler version of the formula. Let's start off with our escape velocity. So what you're about to learn about here is called the Schwarzschild radius, and it's considered a key parameter for black holes. We start off with the equation for escape velocity. Unbeknownst to Carl, he could have got the same result if he had used the Newtonian equation, or unbeknownst at first. And what we're going to do is we're just going to set the escape velocity equal to the speed of light. Carl's idea was that there are two variables in this equation. That's a constant, that's a constant, that's a constant. We could solve for radius or mass. It would be much more interesting to solve for the radius of the event horizon based on the mass of the black hole. In other words, if this is our cartoon picture here, if I know how massive the singularity is, this will tell me how big the event horizon is around it. Arranging for r, we come up with the equation. So we have to square that speed of light, 2gm c squared. And this is known as the Schwarzschild radius. Let's input a 1 solar mass black hole. Typically, they form from 3 solar masses, but let's say you wanted to form a black hole out of the sun. Anything that you compress to this radius, in theory, would form a black hole. So for a 1 solar mass black hole, you would have the Schwarzschild radius equal to 2 times 7 times 10 to the minus 11 meters cubed per kilogram per second squared. The mass of the sun is 2 times 10 to the 30 kilograms. And the speed of light is 3 times 10 to the 8 meters per second squared. Guys, take out your calculator and calculate that while I turn the heat down a little bit. Sorry, Captain, but I've got a... Just for a second. It's like blowing hot air on me when I talk. All right. What do we get?
I got 9.3 to the 11.
That's too big. You forgot to square your C.
All right.
Let's see.
I got three and a bunch of ones.
3,111 meters.
Okay, yeah.
Yeah.
That sounds better than 3 and a bunch of ones because I don't know how big the magnitude is. So 3,000. So how about just 3,000? Is that okay? 3,000 what?
Meters.
How many kilometers is that?
3.
Excellent. The implication of this is that although normally you wouldn't form a black hole from a 1 solar mass object, if somehow the sun could be smooshed into a sphere of radius 3 kilometers, the sun would experience a runaway gravitational collapse from which it could not recover. In other words, if you compress something to its Schwarzschild radius, you can in theory form a black hole out of any mass object. There's a shortcut version to the Schwarzschild radius, which you guys used last week. The Schwarzschild radius is 3 kilometers times the mass of your star in units of solar mass units. So that's mass per solar mass unit. If you have a 3 solar mass star, like a typical neutron star limit, you would get a 9-kilometer event horizon. Keep in mind that if Betelgeuse was to go supernova and leave a black hole in its wake, you would not be able to resolve the central black hole with a telescope. People don't understand, why don't I ever have a picture of this to share? The answer is, to get this resolution, you would need to be able to see a 3 to 10 kilometer size object at a distance of hundreds to thousands of light years away. The best telescopes can barely make out 2 kilometers on the moon, much less 2 kilometers, 600 light years away. So up until we got our first picture of a supermassive black hole, we had never seen this actual event horizon before. More on that in just a moment. Here's a weird thought. In general relativity, there are only 2 full solutions for a black hole. The first is related to the type of black hole that you just described, which is a static black hole. So I'm actually going to erase this here. And now I'm going to try to tell you something really interesting, or something that I find interesting. Let's try you guys out on this. In general relativity, in GR, there are 2 known solutions for a black hole. And that doesn't mean nature only has 2 solutions. That means our mathematical knowledge only permits us to understand 2 types of black holes. The first type, which was described by Carl Schwarzschild, is known as a Schwarzschild black hole. And what distinguishes the Schwarzschild black hole is it's just a singularity, but the important idea is that it is not rotating. It's a static singularity. It's not rotating. We sometimes refer to that as a static black hole. Probably the concept of a static, non-rotating black hole is an absurdity, and try to remember why. Earlier in our lectures, we used this bicycle wheel to demonstrate something called the conservation of angular momentum. Do you remember that? It was how I could make this thing undergo precession and spin around in its axis. One of the things that you learned about when you studied angular momentum is that angular momentum of rotating objects is conserved. And that means mass times velocity times the radius is equal to a constant. Let's assume for a second that you cannot change the mass of a black hole. If it starts off as 5 solar masses, it will stay 5 solar masses. If you cannot change the mass of your neutron star or your black hole, then what will happen to the velocity as the radius contracts to 0 meters?
Wouldn't it have to go up? Like it had to speed up?
In order for that to remain constant, your velocity would speed up. And Arunsak, what's really messed up is, in a black hole, presumably the radius is going to 0, correct? That means the velocity would have to compensate by going to infinity. In other words, a static, non-rotating black hole is most likely not physical. In other words, there's probably no such thing as a black hole which does not rotate. That would imply that it had absolutely no angular momentum to start with, and I just don't believe that. Even our own sun rotates with a 30-day period, right? Now, time for solution number 2. Solution number 2 is known as a Kerr black hole. And this black hole is a rotating black hole. I can't go into all the details of it because some of them I barely understand myself, but I'll tell you this. Something interesting happens to the equations of general relativity when your black hole begins to rotate. Instead of forming a curvature of space-time, which is curved to a single point, that's the Super Mario pit that I told you about before, instead something really interesting starts to happen. As the black hole begins to rotate, and I need just the right picture here, you discover that the equations of general relativity begin to look like this. Instead of the black hole terminating at a single point, a singularity, the coordinates of space-time begin to curve in such a way where the singularity itself disappears, that little dot disappears, and the lines of space and time curve through a fantastical tunnel known as the Schwarzschild throat, and the coordinates of space and time reemerge on the other side of the throat in some unknown location. In other words, this here are regions of normal space and time that could be within our own galaxy or within our own universe. And they are somehow connected through a tunnel to some coordinates of space that are somewhere else. But the somewhere else is unknown. It could be another point in space in our own galaxy. It could be in another galaxy, or it's possible that it even terminates in some other universe. Do you guys know what this thing is called in science fiction?
Wormhole.
That's right. The wormhole is based on a real theoretical calculation that if you force a black hole to rotate, it forms a little tunnel in space and time to some other location, destination unknown. This is really interesting because if there is a large-scale curvature to space, as general relativity suggests, these wormholes are kind of like tunnels between space and time in fantastically different locations. Of course, the writers of science fiction use them to great extent to allow spaceships to travel from one galaxy to another. In reality, it would be quite difficult to do that because if you were even a soccer ball or a basketball and you fell into one of these things, the tidal forces would rip you apart atom by atom. And then don't forget that even if you got through the throat, you could not escape the gravity of the other side unless you could travel faster than the speed of light. As far as we know, nothing can travel faster than the speed of light. So if you fell into the wormhole, instead of being pumped out somewhere else, you'd probably oscillate back and forth until your matter was pulled apart atom by atom, and the increasing energy that the black hole derived would increase the diameter of the throat. You would basically be used and subsumed to become part of the throat itself, rather than travel through. So there's a lot of things for us to work out before we actually can use these as sort of interstellar bypasses or something. But you should know that those wormholes are based on real calculations, and they're quite interesting. The rotating black hole essentially is a wormhole. And that's, something I thought you guys should know about. The one final thing I'll say is that normally black holes form from the collapse of a high mass star. And if the upper limit to a high mass star is like 100 solar masses, one would expect that the most massive black holes could be 10 or even 20 solar mass units, and that's that. It became obvious as we began to study galaxies like our own and other galaxies that there must be extremely massive black holes located at the center of galaxies like our own. And one of the first ways we discovered that is we looked towards the center of our own galaxy, and we saw some images that looked something like this. This is what the closest, you have to look at the center of the galaxy either in infrared wavelengths or at radio wavelengths so that you can penetrate the dust. And if you look at the innermost 1 light year of the Milky Way galaxy, you see this thing which people refer to as a nuclear star cluster. A cluster of thousands upon thousands of stars that are all clumped about some invisible point source. We've been able to study the rotations of these stars, and here's a little animation. They are all orbiting on Keplerian ellipses around some invisible, unidentifiable, unknown source of mass. By using Newton's version of Kepler's third law, we can measure the speeds and the rotations of the stars and estimate what the mass of the central object should be. To date, our best estimate is that there is an invisible piece of matter that's around 3 to 4 million solar mass units at the center of our galaxy. This is what is known as a supermassive black hole. No individual star could form a supermassive black hole. The supermassive black hole would form by the mergers of multiple other black holes, each forming a bigger and a bigger and a bigger black hole. These were considered somewhat theoretical until 2 years ago, when we got our first image ever of a supermassive black hole at the center of the galaxy M87. And this has now become an iconic picture in astronomy. Did you guys see this when it came out a couple of years ago? Sorry. What's so cool is that the image that they got, which was taken at radio wavelengths, actually shows the accretion disk that surrounds the black hole, and you can actually see the event horizon right there. Do you guys see that? That boundary is the event horizon of a real supermassive black hole. This one is actually billions of solar masses. I never thought in my lifetime that I would see a picture, a real picture of an event horizon. Sure, it's blurry and it's grainy, but who gives a shit? That's awesome. It's awesome to be able to see that boundary where light starts to disappear as it infalls into the black hole. That's some of the closest, most direct visual evidence we have of these things existing, and it's palpable and you can see it. And so it's, who knows what future images we may be able to produce now that we've created this image itself. Okay. My friends, I have used up all the time I have with you this semester to talk about stuff in space. I've taught you everything I can. Congratulations for making it through the course. I know, it is sad, isn't it? You can always sign up for Astronomy 1010 or keep in touch. By the way, do you guys know there's a special astronomical event coming up 2 weeks from now?
I do. My grandma emailed me about it. Saturn and something else are going to be like chilling together.
So Saturn and Jupiter will be in conjunction, but this is no ordinary conjunction. Your eye can only see down to 3 minutes of arc, and they are going to be like 3 or somewhere between 3 and 6 arc minutes apart. So it's going to look like Jupiter and Saturn are right on top of each other, and they should make for a really, really bright star. Now, the reason why I'm excited about it is, you know, I've got a small telescope here at my place, and I plan on going up on the peerless roof. And if you put them into a small telescope, we should be able to see Jupiter and Saturn in the same field of view. I've never seen anything like that in all my years of observing astronomy, and I think that'll be a beautiful sight. However, you will still be able to see it even without a telescope. If you look up in the sky, you should see them blur together into a really, really bright star. And with a small pair of binos, like the kind that your pappy might use for bird watching, you might be able to actually resolve them apart. I would love to have you guys to the telescope to see this, but it's probably highly unethical considering that Rhode Island is #1 in COVID cases right now. But at some point, when all of this crap quiets down, I will begin running public open nights every Wednesday for 4 hours after dark. And any one of you and whatever friends or loved ones you have around can come and look through my telescope, and you can see some awesome stuff, and we'll actually get to hang out in the flesh for once. So I would like that day to come, and I'd like you guys to visit the observatory, okay? Besides that, you have no other work to do for me. I'm assuming everyone wants to skip the final and just double their midterm grade, right? That's how we all start.
Professor, I have a question.
Yeah.
The observatory, is that next to Atwell's Ave?
No, it's right at the CCRI campus. It's right in the woods there. So, by the way, there are still some observatories that are open. My friend Scott McNeil, who runs the Frosty Drew Observatory in Innigrad State Park, they have been open, but they have a little more space to socially distance. our administration decided that they, so my observatory, the Margaret Jacobi Observatory, which I am in charge of operating until further notice, is located at the Warwick campus. It's my home away from home. I like to go and escape there during the day. Let's look at CCRI Warwick for a second. If you go to campus ever again, if you're ever allowed to go to campus, when you're coming up the front entrance, and there should be a picture here. Yeah, so when you're coming up the front entrance, you don't go to the temporary parking lot, but, sorry. Okay, this is not what I want. Before you get to the temporary parking lot, there's a left as you come up the entrance that goes down towards the president's house. And about 400 or 500 yards down the road, you'll see a sign for the Jacobi Observatory. It's kind of tucked into a little forest glen. It's really beautiful. So I would love to have you guys there. Spring 2021, as you know, is scheduled to be online. That's probably a good thing until this Corona thing quiets down. But hopefully by next year, if things ever return to normal, then I'll be back there every Wednesday night, and you can come and bring some friends or whatever and look through that telescope. Okay. So yes, I did my best. So you guys have everything you need from me, I believe. Give me an evaluation. Please, Caitlin and Austin, get in your final papers, okay? And
I'm gonna give it all to you, Professor.
Say that? Yes.
I got it all for you.
Okay, that's great. Blast it over to me. I'll try to compute your midterm grades. You guys should already have a pretty good sense of what your grade is, because if you got your midterm grade, as long as you've been doing your homeworks and labs, that's probably quite similar to what your final will be, right? So you can email me for any other details you need, and just have a great break, okay? Stay safe.
Thank you, Professor.
All
Happy
right.
holidays, everybody.
Yeah.
Hey,
Thank all
don't,
you guys. Don't be strangers now. Keep in touch with me. Have fun playing
Professor.
Cyberpunk. Okay, bye.
Arunsak, he's trying to hop off and get on the side.
No, I want to say something to him.
Oh,
Yo,
yeah,
Professor,
What's up?
when the telescope's open, always, you just hit me up through my DMs. I'll pop out Wednesday.
Okay, yeah, because you're in the neighborhood, right?
Yeah.
All right, I will
Yeah.
let you know. I promise. I'd like to hang out
All
with you
right.
guys in person. Okay. Bye,
Peace out,
everyone.
friends.
Thanks for making this
It was a
so
great
much fun.
time. Peace.